I would like to welcome everybody and thank you for joining me in Pure Air to talk a little bit about how to size your odor control dry scrubber. Again, thanks everybody for joining to listen in. Just first off, we'll talk a little bit about myself, and I'm a regional sales manager for Pure Air Filtration. I have been with Pure Air for about 8 years now. I have been in the water and wastewater uh, field or industry for 30 plus years, and I know a little bit about municipal odor control. Um, Talk a little bit here, tell you a little bit about Pure Air. Pure Air was founded in 2004, leader in odor control solutions, and a manufacturer of dry scrubbers in Atlanta, Georgia. And recently we have become part of Clean Water, the Clean Water One company, which is fantastic. And today we're going to go ahead and talk a little bit about choosing odor control systems. Today we will talk a little bit. We'll talk a little bit about our media and media selections, how odor levels and ventilation rates affect the selection of a system. We'll look at sizing a system. We will also talk about choosing the odor control model. And then at the end, we'll look at an example of a selection that we have made. Again, first off, we'll talk just a little bit about our odor control medias. You can see here we have multiple types of media. The first one that we have here is activated carbon, which is good with low levels of H2S and a broad range of gas levels. We use potassium permanganate. Our potassium permanganate medias are great for sulfur compounds and general polishing. Often we mix it with activated carbon to treat gases associated with wastewater and a polishing layer. And we'll kind of get into we have a roughing layer for the H2S and a polishing layer that usually has some potassium permanganate mix in there. We also produce medias for iron oxide, which the iron oxide is used with extreme H2S levels. It exists, for example, high levels that exist, for example, in biosolid applications. And then we also have our high capacity carbon, such as our sulfazorb, which the media is focused only on H2S. And we'll look at a few examples or some examples of the media a little further. We have our absorbents. With our absorbents, the odor molecules are captured in the pores of the media. You can see that we have, our coal-based carbon, our Pure ACX. You can just kind of see some of the things that's porosity. It's excellent, so it's very porous, so it's good for the flow rate. VOCs, great capture for VOCs. Reduced sulfurs, there's poor. H2S. A lot of people think, oh, activated carbon is great with H2S. It's really only 5% per weight. It's where, like, say, our sulfazorb XL comes into play, and we use it for, again, high H2S situations, and it is, good. It's 66% by weight, so it can capture a lot more of the H2S. So again, as far as your dollar goes, you can see here, cost is low. The cost to go after the H2S is very high because you have to use so much of it. And you come down here and you look at our self-absorb, you can see, again, costs might be a little more when you at the initial costs, but cost per pound to get rid of the H2S is low. So it just makes more sense to use that type of our self-absorbed high capacity carbons in high H2S situations. Again, we can see here we have our chemisorb medias. Basically where there's a chemical reaction that changes the properties of the gases and the odors. For example, self-absorb uses a catalyst to hold H2S molecules in the pores of the carbon. Where a lot of times if you use just basic activated carbon, if you have a spike in temperature, which you end up with a spike in H2S, the incoming molecules of the H2S or odor will push out the molecules or odor that are already in activated carbon, and you'll end up with an odor breakthrough, which no city or county or municipality wants that to happen. A lot of times they end up making the newspaper when they get odor breakthrough, and nobody likes that. So, and then we have our blends, blended medias, which are our combination of aluminum spheres treated with potassium permanganate, different concentrations, along with activated carbon. A lot of times, again, I think I mentioned it earlier, we use that as a polishing layer. We'll have a roughing layer, which is basically 2/3 of, say, our self-absorb XL. And then we'll have a polishing layer, which will get rid of the odors that are also associated with wastewater. And after you take the H2S out, all of a sudden you're smelling all these other odors, and that's where our polishing layer comes into play. All right. Let's see. Okay, so we need to know the volume of the room. The volume of the room, the air is going to be pulled from, and the ventilation rate. So here's where we'll talk a little bit about that. There are different air changes rates to keep in consideration when sizing a system. You can see some examples of them right here. A lot of times, and again, these are some of the more common air changes that you see in the wastewater when you're sizing a wastewater system. 3 air changes per hour, which is usually an unoccupied, we'll say it's a remote pump station somewhere where we really don't have a lot of people going in and out of there. 6 is, a moderately occupied, commonly used place where there might be a large pump station where there's people going in and out of it for whatever reasons. So you want the airflow to be a little greater just to clean the air, make sure it's safer for individuals to go in there. We also have 9 air changes per hour. I can say that I have never, really don't think I've ever sized a unit with 9, but I guess some specifications have that in there. And then a 12, which is be like a fully occupied, controlled, declassified place. We'll say a biosolids building where you got a lot of people coming, in and out of there. Again, higher air changes. The more air changes, the better the purification is. Let's see. So here's this formula right here can help you figure out, say, your CFM when you are sizing a system. Here's your air changes that we've been talking about. Then you're going to know your cubic feet or your volume, which again is very important, of the structure that you're pulling the gases from. You divide it by minutes, and that'll give you the CFM that you need to size the system for. Um, Other ways of looking at it is you want to know how much media is going to last a year. We try and size our systems to where media lasts at least a year or more. This formula has, plug in the CFM, your concentration of, say, the H2S. You need your molecular weight of the H2S. This is a conversion factor that we use, 0.00134, to help us solve the issue. Divide that by the capacity of the carbon or of the media, so the capacity of the media can absorb, and then divide that by the weight per, and that gives us the cubic feet per year that we need to size the system. All right, here's some other key. Here's another key in sizing a system, and it's your velocities. Again, your face velocity, feet per minute. In the municipal standard is 50 to 60 feet per minute. You probably see 60 more than is probably the more common. Okay. In municipal situations or with a municipal polisher, say you have a system that is behind a bio scrubber, you can go a little faster because there's less H2S because the bio scrubber has already absorbed a lot of the H2S. So the concentrations going through the polisher are not as high of the H2S. So you can move it a little bit faster, 75 feet per minute. Then the industrial standard, once again, there'll be lower concentrations of, say, H2S. So you can move the air faster, say 100 feet per minute. Another consideration is your empty bed residence time. Okay. Municipal standard is 3 seconds. That 3 seconds pretty much equates to that 60. Okay. So if you're getting 3 seconds residence time, you're going to be at about 60 feet per minute, and and just the opposite. If you're at 60, you're going to be hitting that 3 seconds, which seems to be I don't know, the sweet spot. That's what you see in all the specifications nowadays. Let's see, and let's see, industrial. Well, of course, yeah, and industrial is less as far as, like, we're talking about here. You can go through it a lot faster at 100 feet per minute with your industrial applications, and I think that comes out to be about 1.8 seconds as far as residence time. Here's a couple formulas that we use when figuring out the velocities, or actually figuring out your residence time in these cases. You've got some knowns. In this one, your CFM. So basically, you're going to know your volume, size of the structure you're pulling the air from, times 60 minutes or 60 seconds to 1 minute. The CFM, so divide that, and that'll give you your residence time. Here's another formula. We have, with some of the knowns, we know the feet per minute. We know the depth of the media bed, which most of the time it's 3 feet in the wastewater world. Times that by 60, and that'll give us our residence time. So again, just other tools that we use or formulas that we use to help us size the systems. Let's see here. Let's go to the next slide. All right. This one, choosing the right model. Selections depend on footprint, constraints, and airflow requirements. For example, say I'm sizing a high flow application. I know that these are the choices. Let me step back and talk about our choices. Here we have a VBS, which is a vertical flow system. Here we have a horizontal flow system. We actually call this one our PBS. Here's our VTS, which is higher flow, lower profile, horizontal flow. This one's also a horizontal flow, our PBS. And we have our radial flow, which is more, so it's a radial flow. It's another good piece of equipment or good model for higher flows. For example, say I'm sizing a system and I have a high flow application. Okay, so it's going to be a high flow situation. Multiple VPS systems would work to handle the larger flows, but the VBS systems will take up a lot of space. Okay, so again, this is where that footprint comes into play. But the VBS systems would take up more space than a single VTS unit that can handle the same flow rate with just one system. So again, in that situation, I would probably go with the VTS or VBank horizontal system. Another situation, for this high flow situation, another model we could go with would be our radial flow systems. Radial flow systems are good at handling, the higher air flows that we need for this application. But in this situation, there's a height restriction. So the neighboring community, there's a height restriction, on the equipment that is going to be used at the wastewater treatment plant. So the neighboring community doesn't see the treatment plant. So again, and again, the radial flow, they do a great job, but they are a lot taller than, again, our lower profile VTS system. So again, the VTS just makes more sense in this situation to choose. So let's go ahead and look at an example of the airflow in the overall system that we have chosen. Talk about why we chose a little bit. Again, this is just an overall spreadsheet that we use to help us size the systems. You can see again, here's your media height, your media bed height and length, the depths of the medias, a total of, again, 3 feet. The flow, 27,000 CFM, which is a higher flow rate. And again, here's where we're talking about our velocities. There's our sweet spot, that 60 feet per minute. Again, which is 3-second residence time. Again, those two equate to each other. Static pressures, this actually helps us size the blower and know what the static pressure is externally, the ductwork coming in, and the system. Again, helps us size the blowers. This gives us, of course, the media amount that's going to be needed. You can see here, this is where I was talking about the polishing and the roughing. And so this would be like our roughing section going after the H2S using our high capacity H2S sulfosorb XL media. And again, all the gases that can be detected after the H2S has been absorbed by the sulfosorb. That's where our polishing layer comes into play with our CBS12 blend, potassium permanganate spheres, and the activated carbon blend to get all the other odors that are associated with a wastewater system. Again, something that we try to make sure that our systems will last more than 1 year as far as the media, the consumption of the media. We want the media to last at least 1 year. In this situation, we know we've got 5 parts per million of H2S, the concentration of the gas. And you can see that that'll give us about 2.2 years of life. And that's very desirable for the customer, so they don't have to change out the system as often. Um, that's pretty much it for this presentation. We're trying to make it short and sweet. Just wondering if anybody has any questions at this time.